Alright students, let us continue our discussion from lithium 2. Now from lithium, the atomic number is 3. So you can see here its electronic configuration is 1s2 and 2s1. So you can understand that there are two orbitals in lithium, that is 1s and 2s. So there are two lithium atoms. One we have written here, another we have written here. So we have written here 1s and 2s. In 1s there are 2 electrons, so we put 2 electrons. In 2s there are 1. So for both the lithium atoms we have the similar scenario. Now when 1s and 1s undergo mixing, we get two orbitals, sigma 1s and sigma 1s star. And when 2s and 2s undergo mixing, then we get 2s, sigma 2s and sigma 2s star. Now we have to distribute how many electrons? Since one lithium has 3, two lithiums will have 6. So how do we distribute these 6 electrons in lithium? It will be sigma 1s2, then sigma star 1s2, and then sigma 2s2. So altogether we could distribute 6 electrons. So when we write the MO configuration, it should be sigma 1s2, sigma star 1s2, sigma 2s2. Please make a correction here. I have written MO configuration. It should be MO configuration should be followed by this, and then it will be bond order. How do you write the bond order? Half of Nb minus Na. So how many electrons we have in the bonding MO? We have 2 plus 2, 4 in the bonding MO, and 2 here in the anti-bonding MO. So half of 4 minus 2, that is 1. So you can understand in lithium we have bond order, that is one lithium molecule has one bond between the two atoms. And what will be its magnetic behavior? Its magnetic behavior will be diamagnetic, as all the electrons out here are paired. Then we move to the next molecule, beryllium 2. Beryllium has an electronic configuration 1s2, 2s2. That means just like lithium, beryllium also has 1s orbital and 2s orbital. So we draw the parallel axis, we label E for energy. Then here we have atomic orbitals of beryllium, and in the center we have MO of beryllium 2. So we first draw the atomic orbitals. Here 1s has 2 electron, 2s also has 2 electron with opposite spin. This side similar, 1s2 and 2s2. And then therefore I have 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons altogether to distribute. So we write here sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. Altogether makes it 8. Then we write down the bond order. So bond order is half of Nb minus Na. So here 4 minus 4 makes it 0. So you can understand beryllium 2 doesn't exist. Now since it doesn't exist, no question of its magnetic behavior. So we write magnetic behavior nil. Next we move to boron 2. Boron is the first element in the periodic table which has a occupied p orbital. So boron electronic configuration is 1s2, 2s2, 2px1, or you can simply write 2p1. So altogether we have 5 electrons in boron. So B2 will have 10. So the diagram becomes now a little elongated. You see, you need more space to draw the diagram. So here we write 1s, then we write 2s, and then we write 2p. When we write 2p, don't forget to write 3 blocks here showing px, py and pz. So similarly here also 1s, 2s and 2p. Now we distribute the electrons as per electronic configuration. Now the question arises how the MOs will form. 1s and 1s mixes form sigma 1s, sigma star 1s. 2s and 2s mix form sigma 2s, sigma star 2s. Till here we have been doing for so long, so there should not be any confusion. But the problem arises when we have 2p. Now here we have 3 2p orbitals. Here also we have 3 2p orbitals. So altogether 3 plus 3 gives you 6. Out of 6, 3 should be bonding ammo, 3 should be anti-bonding ammo. So in the bonding ammo, first will be, since till nitrogen, as you know, pi orbital is having lower energy. So here you have to write pi 2px, then pi 2py, then sigma 2pz. These are bonding ammo, lower in energy. And then you have sigma star 2px, sigma star 2py, and highest is sigma star 2pz. Now once you have finished drawing the orbitals, now you distribute the electrons. Now how many electrons we need to distribute? 5 plus 5, 10. So how we distribute? You can see here sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. Now pi orbitals, since they are in the same energy level, they will obey Hund's rule. So it will be pi 2px1 and pi 2py1. So you can see there are 1 unpaired electrons in boron. Now when we calculate the bond order will be half of Nb minus Na. So here we have 6 bonding electrons, you see. 1 2 3 4 5 and 6. So we have 6 bonding electrons and 4 anti-bonding electrons. So 6 minus 4 is 2 and 2 divided by 2 is 1. So in boron molecule also there is one bond between the two boron atoms. And here, since we have 2 unpaired electrons, the bond order, magnetic behavior is going to be paramagnetic. So that's all about boron. Then we move to carbon. C2. So electronic configuration of carbon is 1s2, 2s2, 2px1, 2py1. So we have similar orbitals. So we have 1s, 2s, 2p. Here also we have 1s, 2s, 2p. So in 1s we have 2 electron, 2s we have 2 electron, and 2p also we have 2 electron, but one is in 2px1, another is in 2py1. So when the ammos are formed exactly the same way as before, it will be sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, then pi 2px, pi 2py, then sigma 2pz, then pi star 2px, pi star 2py, and sigma star 2pz. So since each carbon has 6 electrons, 2 carbons will have 12 electrons. So we distribute sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px2, pi 2py2. Okay, so now how to calculate the bond order? The bond order will be half of Nb minus Na, that is half of 8 minus 4, that is equal to 2. And very interestingly here, though carbon has 2 bonds between 2 atoms, but both the electrons are occupying the pi orbital. So here bond order 2, both the bonds are pi bonds. That is an exceptional case. Please have a look. You have to remember carbon 2 does exist in the vapor state, and the nature of the bond between the two atoms is not sigma and pi, both are pi. You can see here sigma 1 is getting cancelled with sigma star 1s. Sigma 2s is also getting cancelled with sigma star 2s. So the 4 electrons needed for 2 bonds to form is solely because of the electrons residing in the pi orbital. That's why the nature of bond is pi here. Then we move to nitrogen. I think nitrogen I have given homework. Please try. You will find bond order in nitrogen will come as 3. As you know, there is a triple bond in nitrogen molecule. Next we move to oxygen. Actually the concept of ammo theory began because of oxygen. You know, oxygen, when we try to explain the formation of oxygen molecule by other theories, we find oxygen to be diamagnetic. But in reality, oxygen is found to be paramagnetic. So no other theory could explain why oxygen is paramagnetic, but you will see in ammo theory how successfully we can explain why oxygen is paramagnetic. So we write the electronic configuration of oxygen. By the way, oxygen is the first element in the periodic table where p orbital starts pairing. Here we have 1s2, 2s2, 2px2, 2py1 and 2pz1. Now for our make our work simple, when we draw the ammo diagram, we will ignore the 1s orbital. Okay, it is there, but we shall not draw. If you wish, you may draw. There is no hard and fast rule, but just to minimize our labor and to save time, we ignore writing the drawing the 1s orbital. But while writing the ammo configuration, definitely we will write. Okay, so I begin with 2s and then 2p. I have not labeled here 2p. Please label. So 2s has 2 electron, 2p has 4 electron, 2s has 2 electron, 2p has 4 electron. Then the electrons will be distributed here. Now since we have 4 plus 2 6, 6 plus 6 12, here we have to distribute. So 2 in sigma 2s, 2 in sigma star 2s. Now here the sigma orbital is lower in energy than pi, which I have mentioned earlier also. So now sigma 2pz, pi 2px2, pi 2py2. Now the remaining 2 will go to pi star 2px1 and pi star 2py1. So the bond order, when we calculate, half of Nb minus Na, that is half of 10 minus 6, which is equal to 4 by 2, that is 2. So we all know that oxygen has double bond in between two atoms, and here also we are able to calculate successfully bond order of oxygen is 2. And very interestingly, we can prove that oxygen is paramagnetic. How could we prove oxygen is paramagnetic? Because of the unpaired electron present in pi star orbitals. Then we have fluorine. By the way, you can notice here in ammo configuration, I did mention sigma 1s and sigma star 1s. Sometimes you may find it's written kk also, because the name of the first shell is kth shell. Now fluorine also we do the same way. Fluorine and neon we do the same way. In neon again you will find the bond order is coming to be 0, so neon 2 doesn't exist. So with this we come to the end of ammo theory. Now few more questions we need to discuss. Thank you.